Hello, my name is Slade Gellin from Buffalo State College in the United States. My paper is entitled Inflated Cushions on a Removing Point Force. My co-author is Romuald Tarczewski of Wroclaw University of Technology in Poland. We've done a series of papers presented at IASS conferences regarding this particular problem, and this is the latest where we have an applied load which is slowly moving over the length of our structure. And here's what our structure looks like. As you can see, it is a modular inflated cushion sewn together. We may have these tension members and cross braces as reinforcements, okay? But ultimately, it's the cushion we're interested in. The problem is we lay it out flat. We attach a cable to the left end. We pull it through a loop at the right end. It will then tent up like you see here into a particular shape, okay? And then once it's in this shape, we will apply load to the structure. Here's the analytical model. Notice we are interested in the overall behavior of the structure. So we're omitting a lot of the details of the actual construction. So we have a point force applied at XF, and we are analyzing it as a nonlinear beam. Here's the equilibrium equation. I say equilibrium because we're assuming that inertial effects can be ignored if we move slowly enough. We are also assuming linear elasticity. We know it's not true, okay, but there's enough nonlinearity that we're not going to worry about it today, okay? When we choose a particular case where we pull the structure so that the horizontal expanse of the deformed structure is 1/2 of that of the total length of the actual structure, and our applied load is 6 times the Euler buckling load. Here is the result with shapes. Essentially what is happening is we have this blue shape. This is the shape before we actually apply any load, or if the load is applied at the end, where of course it would have no effect. It is the shape of the elastica. And then we apply loads. We move along, as you can see, as we go up the length of the structure, we move slowly, okay, and the load goes further and further down. Suddenly we'll rise up and the structure will be symmetric again. And here's the point force under the center of midspan of the structure. This agrees with previous studies. And then it comes back down vertically, okay, and again moves along linearly almost until we return to the right end of the structure. Here is the tension in the rope. We see very clearly that there's 3 domains that we're concerned about. We have this domain, which is near the end of the structure, this domain, which is in midspan, and then a transitional domain where many different things appear to be happening. Okay, this is also seen in the moment. The moment peaks in the transitional range and then relaxes as we go to the middle and then goes back and comes back down again. Okay, here's the position along the span. Essentially what it's saying is in the transitional regions, we could be in a lot of different places along the length of the structure, but the horizontal position of the load is not changing rapidly. So this is non-symmetrical loading of an inflatable cushion structure was analyzed, okay? And essentially we'll have to carry out experiments on a real structure to see if this predictive phenomenon actually works. Okay, thank you very much.